Thank you. Hello everyone, I'm Wuwei Tian from Zhejiang University, Hangzhou, China. My advisors are Professor Jianwei and Liqiang. The previous researchers' presentations were very impressive. Today, I'm glad to introduce you ARTERY, a novel, fast, quantum feedback solution incorporating branch prediction. First, let's define classical feedback. In a conventional computing system, classical feedback allows us to dynamically adjust the input based on the previous output during computation. When it comes to a quantum system, we can still dynamically apply the controlled circuit block according to the low energy state or high energy state from the previous readout. Similar to, to executing if-else programs in a quantum circuit without classical control. Quantum feedback is widely used in quantum applications such as error correction, active qubit reset, remote CNOT gates to achieve long-range entanglement, and quantum random walks. In a superconducting quantum system, quantum feedback is typically realized with low latency IPGAs. The process generally unfolds as follows. First, a qubit is read with, for instance, a 2 microsecond readout pulse. Then, ADC modules capture the readout pulse that carries the qubit state information. The captured data is processed, and the state classification is performed on the IPGA. Once we determine the state, for example, 0 or 1, we can prepare pulses for the corresponding feedback gates immediately on the IPGA. The prepared pulses are sent to TAC modules to produce analog pulses. Finally, these feedback gates are applied to the qubits, completing the feedback loop. However, such a feedback process is inherently time-consuming because a single feedback cycle includes both readout and hardware processing. For example, in Google's demonstration of a circuit-level surface code, approximately 70% of the cycle time is dedicated to perform readout and qubit reset. During this long feedback period, qubits are exposed to various sources of error. Therefore, to reduce the overall time occupied by feedback, it is necessary to either reduce the qubit readout or decrease the hardware processing time on the FPGA. Attempts to reduce readout latency encounter a significant challenge. Reducing readout latency by decreasing the coupling strength also reduces qubit lifetime, known as T1. For example, IBM's fast processor achieves a longer T1 with longer readout latency, while Water, etc. achieved only an 88 nanosecond readout with an extremely short T1. A longer T1 is generally prioritized, making substantial reductions in readout latency difficult to achieve without compromising qubit quality. Similarly, efforts to reduce FPGA processing time also face limitations. Analysis of state-of-the-art feedback methods reveals that previous optimization efforts employing strategies such as parallelism and caching have pushed processing time very close to fundamental hardware limits. Consequently, significantly reducing FPGA processing latency is also challenging. As a result, it appears that both readout latency and FPGA processing time are difficult to curtail substantially. This creates a latency wall in quantum feedback, where the prolonged duration of feedback operations become a critical bottleneck. But what if we could pre-execute the feedback gates? That is to say, if we could anticipate the readout result before the measurement, is fully completed, we could initiate the feedback operations earlier. In essence, by pre-executing gates, we wouldn't have to wait for the entire duration of the long readout and the subsequent FPGA processing latency. The inspiration for pre-execution comes from classical branch prediction. Here's an example of how classical branch prediction works. Consider a branch prediction program with a conditional branch on the left when the variable I equals 2, and previous branch outcomes were not taken, represented as 2 zeros. A branch predictor might estimate that the next outcome will also be not taken. Based on this prediction, the system might pre-execute the instructions corresponding to the not taken branch before the actual branch condition is evaluated. If the prediction is correct, the program continues seamlessly. If incorrect, the pre-executed instructions are flushed, and the branch recovery mechanism redirects execution to the correct path. Inspired by this classical method, quantum gates can similarly be pre-executed and, if necessary, recovered from. However, classical branch prediction cannot be directly applied to quantum feedback due to the inherent readout randomness. For example, if a readout distribution shows a high probability of being in one state, the state of the next shot is easy to predict. But when marrying a qubit state with a near 50-50 probability distribution, it is hard to predict the next shot. Furthermore, the readout process itself generates a continuous stream of information over time, which classical predictors typically do not utilize. Thus, while gate pre-execution is a promising strategy, a new quantum-specific branch prediction design is necessary. The figure shows the state classification process. A readout pause after the demodulation yields a classical state. What if we demodulate pauses within smaller sequential time windows? By demodulating segments of the readout pause over these small windows, we can trace the evolution of the measurement signal on the IQ plane. These are the readout trajectories. For example, T0, T1, then T2, T3, T4, and T5. We can observe that the trajectory corresponding to the zero state moves towards center zero region in the IQ plane. And similarly for the state 1 towards the center 1 region. Therefore, the evolving trend of these readout trajectories can provide early indications to help predict the final quantum state classification. Classical branch prediction often uses a branch history table to record historical outcomes, serving as prior knowledge, and ARTERY follows this way. For example, at time T2, if a historical state record indicates a sequence like 1, 1, this suggests a higher likelihood of the current branch being branch 1. Consequently, we might pre-execute branch 1 operations. As for quantum readouts, we obtain prior probability, p-history, and historical shot trajectories to form the trajectory state table. For the current shot, the path is partially demodulated, and the states of different time windows are recorded as a vector. For example, states at T0, T1, and T2 are gathered to generate the vector 0, 1, 1. When we use this vector as an index to consult the trajectory state table, we can obtain the posterior probability, P-read. By employing a Bayesian network to hybrid this posterior probability with the prior probability, we derive a joint probability. If this joint probability exceeds the predefined threshold, we proceed with pre-executing the corresponding branch gates. This slide presents an overview of ARTERY's hardware design implemented on an FPGA. The feedback controller on the FPGA interfaces, on the one hand, with an add-on card equipped with DACs and ADCs via SerDes links. On the other hand, it connects to other FPGAs via a backplane. Here is a more detailed look at the hardware design. The upper section contains a state classification and readout prediction unit. The middle section houses a dynamic timing controller. The lower section contains a branch decider and path preparation unit. This dedicated hardware design is crucial because quantum feedback is extremely latency sensitive. So the method has to be evaluated on the FPGA. Because our prediction mechanism is dynamic, static timing for execution is no longer optimal. Previously, instructions might have been wait for a fixed feedback time, then execute the quantum gate. With ARTERY, from static to dynamic, the control timing needs to be modified to execute feedback operations based on a trigger generated upon successful predictions. For example, at time t0, if a predicted probability is below the threshold, gate pre-execution is not initiated. At the next moment, the predicted probability exceeds the threshold. Then, the dynamic timing controller issues a feedback trigger. This trigger is received by the feedback decider, which decides gate pre-execution. If other FPGAs are involved, they need to wait for signal transmission before doing gate pre-execution. This table illustrates the feedback latency improvement achieved by ARTERY. And this shows ARTERY's fidelity improvement due to feedback latency reduction. Overall, ARTERY achieves a 2.07-fold feedback latency reduction and a 1.24-fold fidelity improvement compared with the state-of-the-art method, with over 90% of prediction accuracy. We propose the first branch prediction method specifically tailored for quantum programs. By the way, the physical implementation of ARTERY is based on superconducting quantum systems. However, the mechanism can be generalized to other physical implementations, such as neural atom and trapped iron hardware. ARTERY kind of breaks through the latency wall of quantum feedback. That's all. Thanks very much.